Resolving power of optical instrument. The resolving power of optical instruments affected by diffraction at objective lens. We have already studied the diffraction at circular aperture. Now here the optical instruments are like microscope, telescopes, which consist circular lenses, which we are calling objective lens. And when light is passed through this objective lens, we get the diffraction pattern. And if the two images, when we are watching through the telescope, two images, if they are very close to each other, then what happens? The diffraction pattern of image 1 overlap with diffraction pattern of image 2. Suppose this is the diffraction pattern of image A, and let us say this is the diffraction pattern of image B. If A and B are very close to each other and we are watching these two A and B through the telescope, and while watching it we get the diffraction pattern of these two objects. If these two objects are very close and if their diffraction pattern overlaps, then we cannot distinguish between these two objects. It will appear as a single object. This is particularly important in case of astronomy. When we are watching through the telescope at two stars, and if the separation between the two stars is very small, then what happens? The diffraction pattern of these two stars overlaps, and we cannot distinguish these two stars. For us, it will appear as a single star. So, what is the resolving power of then optical instruments? Resolving power of optical instruments is defined as its ability of optical instruments, which is expressed in the numerical value, to resolve nearby objects or images. That ability is called the resolving power of optical instruments. Similarly, we have used prism and grating also. Through the prism or through the grating, we can see different spectral lines of different wavelengths. Like, you can see the green light, uh, blue light, red light, like that. When white light is passed through the grating, we can see the spectrum, and that spectrum consists different wavelengths of different colors. Then the resolving power of optical of this prism, resolving power of prism or grating, is defined as similarly ability of a prism or ability of grating, which is expressed in the numerical value, to resolve nearby spectral lines. So ability of prism or ability of grating to resolve nearby spectral lines, which is expressed in the numerical value, is called resolving power of prism. So this ability actually we have to express in the numerical value. Then there was a scientist named Lord Rayleigh. This scientist proposed arbitrary criteria to express resolving power of optical instruments in numerical value. What this Lord Rayleigh did, he proposed arbitrary criteria to express resolving power of optical instruments in numerical value. This criteria can be applied to, of course, microscope, telescope, grating, prism, etc. etc. So let us see what is this Lord Rayleigh's arbitrary criteria to express the resolving power of optical instruments. There are three different criteria, and the first one is, as you can see here, A and B. These A and B are the central maxima of the diffraction pattern of two wavelengths whose wavelengths are lambda 1 and lambda 2. Say wavelength of A is lambda 1, wavelength of spectral line A is lambda 1, and wavelength of spectral line B is lambda 2. And what you see in this case is A diffraction pattern of wavelength lambda 1 and B the diffraction pattern of wavelength B of spectral line B. So in this case we are considering two spectral lines A and B whose wavelengths are lambda 1 and lambda 2. What you see in this diagram is their diffraction pattern. Now here in this case, the angle of diffraction of central maxima, as you can see here, this is the central maxima of spectral line B. And let's say whose angle of diffraction is theta 1. And angle of diffraction of the first minima, this is the first minima of spectral line A. And that angle is, let's say, theta 2. Then if the theta 1 is much larger than theta 2, then you can say that these spectral lines A and B are well resolved. In this diagram, we have diffraction spectra of spectral line A, whose wavelength is lambda 1, and diffraction spectra of spectral line B, whose wavelength is lambda 2. Theta 1 is diffraction angle of central maxima of spectral line B, and theta 2 is diffraction angle of first minima of spectral line A. And if theta 1 is much greater than theta 2, then we can say that these two spectral lines A and B appears as well resolved. So this is one of the Lord Rayleigh's criteria for well resolved spectral lines. So we got it when we can say that the two spectral lines are well resolved. Then second criteria is, as you can see here again, there is a spectral line A and spectral line B. Wavelength of spectral line A is lambda 1 and wavelength of spectral line B is lambda 2. And the difference in wavelength lambda 1 and lambda 2 is small. And then what happens in this case? The difference in wavelength is such that the diffraction maxima of spectral line B center of this diffraction maxima. This is, let's say, theta 1. That the central maxima of spectral line B coincide with first minima of spectral line A. As you can see here, at this point over here, this is the center of central maxima of diffraction of spectral line B, which is also equals to the first minima of diffraction pattern of spectral line A. So difference in wavelength of spectral lines A and B is such that the position of spectral maxima, or you can say here also, consider A. This is the position of central maxima of spectral line A here, which coincides with position of the first minima. This one is also the first minima of spectral line B, and vice versa. So when central maxima of one spectral line coincides with the first minima of another spectral line, then you can see the resultant intensity as hump. You can clearly see here hump here, two hump for A and B. So resultant intensity curve shows double humped curve with a clear dip over here. There is a clear dip at the center of the two central maxima. If this is the case, then you can say that the spectral line A and B are just resolved when central maxima of one spectral line coincides with first minima of another spectral line, or vice versa. Then it is called that two spectral lines are just resolved. So this was the second criteria. Then what is the third criteria? As you can see, the third criteria is unresolved. When we can say that these two spectral lines A and B are unresolved. Difference in wavelength of spectral lines A and B is so small that central maxima of wavelengths A and B are sufficiently overlapping. You can see here, this is the central maxima of the B and this is the central maxima of A. And these two are sufficiently overlapping. If they are sufficiently overlapping, then resultant intensity curve shows only one maximum. There is no diff. So you will see only one maximum. If this happens, then you can say that these spectral lines A and B are not resolved at all.